Right here, the notes for section 4, real zeros of polynomials. So long division first. So let f of x and d of x be polynomials with the degree f greater than or equal to the degree of d, and d of x not equal to 0, because you can't divide by 0. Then there are unique polynomials q of x and r of x, called the quotient and the remainder, such that the original function is equal to the d of x times q of x plus r of x, or either r of x equals 0 or has a degree r that is less than the degree of d. So the thing you're dividing is called the dividend. The thing you're dividing by is the divisor. If r of x, the remainder function, is equal to 0, then it divides evenly. And sometimes you'll see this written in fraction form like this. So example 1, use long division to find the quotient and remainder when 2x to the fourth minus x cubed minus 2 is divided by this. So 2x to the fourth minus x cubed minus 2 is being divided by 2x squared plus 2x plus 1. So to do long division, the number that goes here is what I need to multiply 2x squared by to get 2x to the fourth. Or if you want to think about the other way, 2x to the fourth lead term divided by lead term. That's going to be x squared. So now what I do is take this x squared times all of these terms. So 2x to the fourth plus x cubed plus x squared. And then I subtract all of that stuff. So 2x to the fourth minus 2x to the fourth is 0. Negative x cubed minus x cubed is negative 2x cubed. This guy is going to slide in here, and then the negative 2 comes down. And now I just repeat the process. What do I multiply 2x squared by to get negative 2x cubed? Well, I need to multiply negative x. So negative 2x cubed, that's going to be negative x squared, that's going to be negative x. And then I subtract all that again. So those cancel, means negative x squared minus negative x squared is negative x squared plus x squared. So I have x minus 2. And now I can't go any farther because I can't multiply 2x squared by to get that. So written in terms of the summary statement, we would say our original function, 2x to the fourth minus x cubed minus 2 is equal to the divisor, 2x squared plus x plus 1, times the quotient plus the remainder. So written in fraction form, that's going to look a little bit different. It's going to be f of x over d of x. So f of x over d of x is just going to be, let's see here, 2x to the fourth minus x cubed minus 2 over 2x squared plus x plus 1 equals the quotient function, which was x squared minus x, plus the remainder function over what we divided by. So these two things are equivalent. Normally you'll actually see it written in this form, but they are both technically correct. That's long division. Okay, so now I've got the remainder and factor theorem. So it says find the remainder, if a polynomial is divided by x minus k, so this is just a binomial of degree 1, then the remainder is whatever you get when you plug the k value in. So k value is what you're subtracting for x. The other way to think about it is the value for k is what makes this expression equal to 0. So for this problem, k is 2. For this one, k is going to be negative 1. For this one, k is going to be negative 4. So to figure out what the remainder is, I plug these numbers into my equation. So 3 times 2 squared plus 7 times 2 minus 20. So calculator, 3 times 4 plus 14 minus 20, this is 6. The remainder will be 6. If I do negative 1, so fill in negative 1 becomes x's, so that's 3 minus 7 minus 20, so that's negative 24. And then the last one, if we plug negative 4 in, 3 times negative 4 squared plus 7 times negative 4 minus 20. So that's 3 times 16 minus 28 minus 20 is 0. Now, since this last one is 0, that actually means that this is a solution to the equation. So a polynomial function has is a factor of, I should say. So x plus 4 is a factor of 3x squared plus 7x minus 20. So it goes in evenly because it has no remainder. So for a polynomial function f and real number k, the following statements are equivalent. X equals k is a solution. of f of x equals 0, so that was this case here. K is a 0 of the function, k is an x-intercept, x minus k is a factor, so they all mean the same thing. Now, long division gets to be real tedious, so instead we have what's referred to as synthetic division. So divide 2x cubed minus 3x squared minus 5x minus 12 by this using synthetic division. Now, the one thing about synthetic division is that you have to have all of the terms present. So if you're missing any, you have to fill zeros in. And you put outside the value for k. So what I actually do is I copy down my coefficients. So 2x cubed, negative 3, negative 5, and negative 12. So those are my coefficients. I'm not missing any values, so I don't need to fill any zeros. And then in the box, I put my value for k. Now leave yourself some space. So what happens is the first coefficient drops down, 2. 3 times 2 is 6. Add down is 3. 3 times 3 is 9. Add down is 4. 3 times 4 is 12. Add down is 0. Now these numbers are now the coefficients of a polynomial that's less by 1 degree. So this is 2x squared, because I originally had cubed, and then everything is just descending order. So 3x plus 4, the last number goes away because it's actually the remainder. If you did, technically it's 0 over x minus 3, so the remainder divided by what you divided by. But since it's 0, this term would just typically disappear. So that is the quotient when you divide this by that. Much easier to do. And since it goes in evenly, that means this is a factor of that. Okay. Rational zero theorem just says that if you have a polynomial, all of the possible rational zeros, meaning decimals are repeating or terminating fractions, is found by taking the factors of the last term divided by the factors of the initial term and all possible combinations. So here it says find the rational zeros of this expression. So my value for p is 1, my value for q is 1. So the factors of 1 are just 1. The factors of here are just 1. So my possible solutions are plus or minus 1, because it's always plus or minus. Blah, 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 blah. If p over q is a rational zero of f, p of q, no blah, blah, blah. Then this is true. So if I can check, I just plug them in. So 1 cubed minus 3 times 1 plus 1, and I do the same thing with negative 1. So that's 1 minus 3 plus 1. Well, that's not 0, so that's not a solution. And down here, this is negative 1 plus 3 plus 1, which is also not 0. So neither of those solve it, but these are the only possible rational solutions, which means this equation has no rational roots. All right, so for example 5 here, so we got this 3x cubed minus 4x squared minus 5x minus 2. So we need to find the possible rational roots first. So for p, our factors of 2 are 1 and 2. For q, our factors of 3 are 1 and 3, and then we have to do all possible combinations. So 1 over 1, so plus minus 1. 1 over 1, 3 is plus minus 1/3. 2 over 1, plus or minus 2. 2 over 3, plus or minus 2/3. So these are the possible solutions. So what we're going to do is, normally you can look at the graph and see which ones approximately work. If you look at the graph of this original expression, you'll see that 1 is a likely solution. So I'm going to do synthetic division with 1. So 3x cubed, 4x squared, negative 5x, negative 2. So 1 times 3 is 3, that's 7. 1 times 7 is 7, that's 2. 1 times 2 is 2, that's 0. So this would be 3x squared plus 7x plus 2. Then that's a quadratic that I just run the quadratic on. So if you work that out, your solutions actually end up being x equals 1, x equals negative 1/3, and x equals negative 2. So all of them are actually contained in this list. So upper and lower bounds, a number k is an upper bound if f of x is never 0 when x is greater than k, meaning the values never come back down. Number k is a lower bound if f of x is never 0 when x is less than k. So that means once you go past k, you never hit 0 again. Once you go more than k, you never hit 0 again. The graph keeps climbing or falling. So here's the rules. So let f be a polynomial of degree n more than 1 with leading coefficients. Suppose f of x is divided by x minus k using synthetic division. If k is more than 0 and every number in the last line is non-negative, meaning it can be positive or 0, so it doesn't say positive here on purpose because it could also be 0, then k is an upper bound. If k is less than 0 or equal to, and the numbers in the last line are alternately non-negative and non-positive, then k is a lower bound. So once again, careful of those words. Non-negative doesn't actually mean positive, because non-negative is positive or 0. Non-positive is negative or 0. So prove that blah, blah, blah. So we'll do synthetic division with 5. So my coefficients are 2, -7, -8, 14, and 8. And we'll do the same thing with -2. 2, -7, -8, 14, 8. So drop the 2 down. 5 times 2 is 10. So that's 3. That's 15. So 7. That's 35, which is 49. And 5 times 49 is 5. Carry the 4, 245. So this is 253. So these values are all non-negative. They're either all positive or 0. So 5 is the biggest. There are no zeros more than 5. Over here, similar pattern, drop the 2 down. So that's -4, which makes -11. That's positive 22, which makes 14. That's negative 28, which makes -14. That's positive 28, which makes 36. So these are alternating non-negative, non-positive. So that's not negative, that's not positive, that's not negative, that's not positive, that's not negative. So -2 is the lower bound. There are no zeros less than -2. So all my solutions have to lie within that bound. All right, so example 7, find all the real zeros of this guy. So we'll do our P and our Q first. So P is the factors of 8. So 1, 2, 4, and 8. Q is the factors of the lead coefficient, 1 and 2. So our possible solutions are plus or minus 1, 1 over 1, plus or minus 1/2, 1 over 2. 2 over 1 is 2. No, 2 over 2 is 1. I already have it, so I don't need to do that one. 4 over 1, so plus or minus 4. 4 over 2 is 2. I already got it. 8 over 1 is 8. 8 over 2 is 4. I already got it. So these are the possible rational solutions. So what I would do is I'd either pick one randomly. I could find one that looks like it works on the graph, and then go that way. So let's try 4, because why not? So if we do 4, also because I know what the answers are, coefficients are 2, -7, -8, 14, and 8. So drop the 2 down, that's 8, which makes 1. That's 4, which makes -4. That's -16, which makes -2, which makes -8, which is 0. So that worked. Now the thing is, if I want to now check, let's try, what's the other solution that's going to work? -1/2. So the thing is, I don't need to rewrite the problem. I can just slap the -1/2 on and repeat the process. So 2 falls down, -1/2 times 2 is -1. That's 0. That's 0, which makes -4. -1/2 times -4 is +2, which is 0. So these two guys both work. So I know I have an x minus 4 as a factor. I know I have an x plus 1/2 as a factor, because remember, it's the opposite of these things. And down here, this was x to the 4th, which means that's x cubed, which means this is x squared. So the last factor is 2x squared minus 4, because there's no x. Then I can solve that guy with algebra. So 2x squared minus 4 equals 0. 2x squared is equal to +4. X squared is equal to 2, which means when I take the square root, x is equal to positive or negative root 2. So my solutions are 4, -1/2, plus minus root 2. All right, so 8, prove that all the zeros lie in the interval, and then find them. So this is the bigger one, so we'll do 1. So our coefficients are 10. So now I'm going to have to fill in missing values. That's x to the 5th. I have no x to the 4ths, no x cubes, -3x squared, 1, -6. Since that's a 5th power, there has to be 6 terms here. The 5 exponents and the 1 constant term. So the 10 falls, that's 10, which is 10. 1 times 10 is 10, that's 10. 1 times 10 is 10, that's 7. 1 times 7 is 7, that's 8. 1 times 8 is 8, that is 2. All non-negative. So this is the biggest value. There are no zeros more than 1. Then here, if I do the same thing, so 0, 0, -3, 1, -6, 10 follows 0, 0, 0, 0, 0, 0. Whoops, nope. 0 times 10 is 0, adds to 0. 0 times 0 is 0, adds to 0. 0 times 0 is 0, adds to -3. -3 times 0 is 0, adds to 1. -0 times 1 is 0, add down is 6. So alternating, not negative, not positive. Not negative, not positive. Not negative, not positive. So the pattern works. Not negative, not positive, not negative, not positive, not negative, not positive. So that's the least. So all our solutions are between 0 and 1. Now, if you actually look at the expression, there are no, well, here, we'll come up with the rational possibilities first. So P, Q. So P is the factors of 6, so 1, 2, 3, 6. Q is the factors of 10, 1, 2, 5, 10. So we've got 1 over 1, we've got 1 over 2, we've got 1 over 5, we've got 1 over 10. So that's the 1 with all of them. And we've got 2 over 1, so plus minus 2. 2 over 2 is 1, we've already got that. 2 fifths, 2 over 5. And 2 over 10 is 1/5, we already have it. So 3 over 1 is 3, 3 over 2 we don't have, 3 over 5 we don't have, and 3 over 10 we don't have. And then we go to the 6. 6 over 1 is 6, 6 over 2 is 3, we've already got it. 6 over 5 we don't have, 6 over 10 is 3/5, which we already have. So these are all the possibilities. If you actually look at the graph, none of them work. From the graph, the only solution that does work is not a real number, or not a rational number, it's 0.95. That's the actual only solution that works. But these give you a good place to start. Which brings us, I believe, to the end of the section.